Alrighty, good morning, everyone. First off, I must profusely apologize for missing this morning's lecture. Like I said, I'm a bit under the weather. Also, the reason I'm doing this on Pear Deck, as you guys can probably see, is purely because, it's been one of those weeks. So because I got sick and I wasn't expecting it, I forgot my tablet at school. So we're going to have to make do with this. If you have questions, as always, feel free to message me and ask about a writer time, and we can set something up. But today what we're going to do is we're going to talk about integrals as area under the curve. The idea is that you have antiderivatives. They're operations, and integration is the application behind that. Derivatives give you a slope, and integrals give you the area under the curve. When you're doing antiderivatives, that gives you the equation that you can use to find your area under the curve. But again, that's kind of the main difference. But when we're talking about area under the curve, the two things that we're looking at is total amount or area under curve. This is kind of how it's going to appear when we're doing AP exams and stuff. So it'll say, what is the total population? Or what was the total amount of money that you earned? Or if they'll say something like ballots are coming in and every hour you get a certain amount of ballots based on this function. What were the total ballots that came in? So basically you have to add all the little parts together and then you're doing area under the curve. Again, we're going to talk about that a little bit more in the future when we're talking about word problems. But for today, the main idea is when you're doing antiderivatives, you're doing an operation, and when you're integrating something, you're finding the total amount of something that's coming in, but graphically you're finding the area under the curve. Okay, that's kind of the main thing that we're doing here. So first off, the main thing is we're finding the area under the curve. So basically what that's going to look like is if I were to say from here, let's actually use our line tool to make it a little easier. If I were to block off from here, and 0, and I were to say find the area of the curve, basically what I'm looking for is what is the area of this space over here. And then this is some sort of positive space, so it'll be something like 15 or 7.36925 or something like that. But we're looking at the area of this weird bowled out shape. And from what you guys remember from geometry, there's a lot of ways that we can do this, where we have like circles and we have arcs and triangles cutting out of them. So there's a lot of different things that we can do. But basically, I'm looking for the area under this curve. And what we mean by that really is basically, if I were to again bind this off, we're saying what's the area that's bounded between the curve and my x-axis. So if I were to take it from here as well, we have this. And as I mentioned previously, this was positive, this was negative, and since this is a cubed function, they'll actually cancel each other out. But again, the whole idea is we're saying based on a certain interval, what is the area under the curve? And again, we're looking at this graphically. That's the main idea. So the way that we're going to do this is we're going to approximate this using geometric shapes. So again, if I were to say something like, I want the area under the curve from 0 to, let's use notations, 0 to, I don't know, 4 or something like that, then what we would do is we would say, okay, we're going to start at 0, bind it to the x-axis, move up to 4, bind it to the x-axis, and then we're looking for all of this area over here. Okay? And what we're going to be doing today is we're going to show you how to approximate it. Now, you know how to actually find this. The way we actually find it is we do integral from 0 to 4 of f of x dx. And this is your exact. But again, what we're going to do today is we're going to talk about how to approximate. And the way we're going to approximate it is using different geometric shapes. So let's get into our first way of doing it. So that's where something called Riemann sums comes in, and summation notation. Okay. This is going to be what we're going to be referring back to for all of our problems. However, I'm going to explain the context of each. So don't worry about copying this down again. I'll post the PowerPoint that I'm using as well, but don't worry about that too much for now. This is just something we're going to come back to. It looks really ugly, but there's a really easy way to read it after. So basically, here's what's going on. There are rectangle approximations, and what rectangle approximations do is they draw rectangles, and they say, okay, here's rectangle 1. Here's rectangle 2. Here's rectangle 3. here's rectangle 4. And if I find the area of all of these 4, black, pink, orange, and like light blue, if I find the area of this, we can add them all up together, and then we can approximate the area of the curve. Now, as you can see, this is a pretty junk approximations, because if I was to look at green, if I was to look at this green area over here, and I'll just highlight it, this green highlighted area is all of my missing, right? All of this is being left out, and that's actually quite a lot because of the way the shapes work. So that's not the best approximation, but it's just an approximation. We're just saying approximately what's the area under the curve. So the reason why we're breaking it down into rectangles is because it's easy to find the area of rectangles. So idea is that rectangles area is easy to find. And when you're looking at the area of a rectangle, the main thing that you're doing is the area equals base times height. That's the two things that we're dealing with. Now, if you're looking at that, the base of this is 1. 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 And the height, what is the height of this? Basically, what we did is I started at my function here, and then I just drew a horizontal line across. So if we know what f of 0 is, we know what the height of this is. So this height is f of 0. This pink height over here, I started at the function at 1 and I drew a horizontal line across. So this is f of 1. Again, that's the height of this. Even though I'm putting it on the right side, we're using the left. The height of this orange one is, again, f of 2. Whoops, we'll make this pink. The height of this orange one is f of 2. And basically, that's what we're doing over here. We're saying, how do we find these heights? And the way we find the heights is we start off on our function, we draw a horizontal line across and go down. And again, the way we find the height of this function is this here is my y value when x is 0, which is literally defined as f of 0. So that's how we find our height over here. So again, this is one approximation here. What I have drawn out is called your left-hand approximation. And the reason it's called your left-handed or left-sided approximation is because you're starting at the left and you're drawing your lines across. So again, basically the main idea here is you're drawing rectangles where the left corner, sorry, let me adjust this really quickly. Where the left corner is on your function. Okay? And again, to find the area of this black thing, you're going to do area equals, let me make my text just a tad bit smaller. Area equals base times height. And in this case, your base is 1 and your height is f of 0. Same thing here. Your area of this pink one equals base, which is 1, times by your height, which is f of 1. And again, the way we get that f of 1 is we're just saying, what is the y value on the left side of this rectangle if it were to touch this function? And again, this is not a good approximation. The reason it's not a good approximation is we have all of this missing little pieces here. So it's underestimating. So let's say we add all this up and we get something like 15. We're still missing all of these little green parts. So it might be something like 16 or 18 or there's a lot of things that we're missing. But again, that's why it's in approximation. It doesn't need to be neat for now because what we're doing is we are just getting the general concept, and we're going to tighten this up after. So let's actually do this orange one. So my area for this orange one, my area is going to be equal to 1 times by f of 3. And in this case, f of 2. So f of 2 is going to be 1 over 7 parentheses 2 minus 2 raised to the third power raised to the third plus 3. And I'm going to just write this up here so it's easier for us to see. This becomes 0, so area equals 1 times by 0 plus 3. And then so my area equals 3. And again, basically this is the whole idea, is we're saying what is the height of my rectangle. Let's use my function, which my function was written up here in case you didn't notice it earlier, and my base, which I just split it into 4 equal parts, so I went 1, 1, 1, 1. Okay, so again, we're just going to find the area of this, area of this, area of this, area of this, add them all up, and that's what we're going to be getting. Now, that's where this comes into play. Okay, this ugly thing here, this is just your basic what's called summation notation. Okay, summation notation. And what summation notation is doing is it's saying, how can we write a bunch of sums all together at once? Now let's look at this over here. What we're saying is, I want to find the area of this plus the area of this plus the area of this plus the area of this, and that's all we're doing here. So we're gonna say area of triangle. So I'm gonna write this A1, that's the area of triangle 1, plus area of rectangle 2. I'm not sure why I said triangle for the first time. Area of rectangle 3 and area of rectangle 4. Okay, that's what we're looking at here. Area of rectangle 1, area of rectangle 2, area of rectangle 3, area of rectangle 4. And that's going to be my summation approximation. Now, if you read through the lines, that's all this is saying here. What we have here is this is our y value of our first point on the graph. That's what that f of x1 is saying. And again, if we looked over here, that's this, f of 1. And then we're timesing it by change in x. Now, if you remember, change in x is saying, how much did my x's change? And so that's basically interpreted as our base. And then since we're splitting all of them into equal pieces, equal piece, equal piece, equal piece, equal piece, that means all of the bases are going to be the same. So one way that you can find the base length is equals total interval divided by number of intervals. And that's how you find your base length. Total of intervals times number of intervals. So again, what we have here is this first section here. This is your first base. Second, we have this over here. This is your base length. So this is base times height, base times height. And we're just going to keep doing that over and over and over until we do all of our little rectangles. That's what this notation is doing. Now let's wind it back up to here, and then I'm going to pull everything together. Whoops. So let's clear this. So here's what's going on. This here is called sigma. It's just a Greek letter, and then the sigma is used to represent a bunch of sums. So basically, this is the reason it's called summation notation, is this is the notation we use when I'm adding a bunch of things together, and they all follow the same pattern. Excuse me. But that's what sigma is. It's used to represent a bunch of sums that follow the same pattern. So what this is telling me is that I'm going to add a bunch of things. I'm going to start at x1, and then I'm going to keep going till I hit x to the n. So if you look, I went x1, then I added it to x2, then I added it to x3, and all we're doing is we're taking this I value and we're increasing it on the integers until I hit n. So I'm starting at 1 and I'm ending at n, and that's really similar actually to your integral symbol. So if we had something like 3 to 5, then you would start at 3 and end at 5 kind of deal. Sort of, kind of, basically. But realistically though, what we're doing is if I went 3 to 5 and I needed 4 spaces, this would start at 1 and this would end at 4. I'll explain that in just a minute though, I promise. Okay, so again, the whole idea here is that this summation notation here, this sigma notation is used to compact all of this into a neat little form. So this here tells you we're going to add And we're going to use this pattern, and we're just going to replace the I starting at 1 and ending at n. So for example, if I were to use something like this, oh gosh, we're going to have to draw this very ugly. So we use sigma of I equals 1, and we're ending it at 3 for f of xi, change in x, we're going to draw a tiny little triangle here. Okay, if I were to do something like this, then what this is going to come out to is f of x1 times change in x plus f of x2 times by change in x plus f of x3 times change in x. And again, all of these are going to get their little triangles here. Okay, and again, that's all this does. This just packs this pattern up. That's what your summation notation is doing. And again, so we'll use that to find the area under here. And so we're going to use this little summation notation in order to find the area of this. And again, that's purely notation. Ideally, what we're doing, though, is we're adding a bunch of triangles together until we estimate the area under the curve. All right, now with that being said, let's talk about the difference between left-hand and right-hand approximations. So left hand is obviously you're starting on the left and then you're making a horizontal line. You're starting on the left and you're making a horizontal line. You're starting on the left and you're making a horizontal line. And then you're just finishing up your boxes. Whoops, sorry. Let me actually use the line tool so it's a little nicer. So again, we're starting on the left, making a line. 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 And then we just draw down. And then that's how we find our little rectangles that we're taking the areas of. This is left approximation. Right is going to do the same thing, but we're starting at the finish line and we're coming backwards. So this is how we draw my first one. This is how we draw my second one. This is how we draw my third one. This is how we draw my fourth one. And as you can see, last time we undershot by a lot. This time we're overshooting by a lot. So you can see there's all of this here that shouldn't be under the curve, but we're including in our approximation, which is why these left and right-handed Riemann sums are not entirely extremely accurate. So one of the most common questions they're going to ask is this an over or under approximation? So all you do is you just draw out your shape, and then you see, well, I'm catching more than I need to get. So because of that, it's going to be wrong. Again, my area that I should be looking for is this area under the curve here. So I'm just going to highlight it like this. This is what I'm looking for. And all of this blue is just extra. Okay. So that's the difference between my rectangle approximations. We have left hand, which we start on the left and make our horizontal line to make our rectangles, versus right hand, we start at the end and come backwards, and then we work from our right. So that's the main difference. Next, we have midpoint approximations, which, as you guys can assume, you start at the midpoint and then you make a horizontal line that way, and that's how you get it. The reason why this one's kind of nice is because, generally speaking, it's normally a little more accurate because it overestimates a little and it underestimates a little. So this is a lot more accurate, as you guys can see if I could actually draw nice lines. But this is a lot more accurate where I'm not like crazy overestimating or crazy underestimating. In fact, it almost looks like my underestimation and my overestimation, or underestimation and overestimation, cancel each other out or close to it. But again, it's still just an approximation. So all midpoint approximation does is to find the height of your triangle, use the midpoint of your rectangle. Okay, that's all it is with midpoint approximation. Okay, trapezoid approximation, again, does something really similar where it says we're going to start and just take the start and end points of each of my things in order to make these trapezoids. So here, I'm going to have trapezoid 1. Then I'm going to do this one in green. Then we're going to have trapezoid 2. Then we're going to have trapezoid 3. And then finally trapezoid 4. And again, as you guys can see, it's a lot more accurate than left or right hands. Some would say maybe it's a little worse than midpoint. Some would say it's better. But again, it just depends on what curve you're kind of looking at. But regardless, this is just another thing. Now, one thing you have to remember is what is the area of a trapezoid? And the area of a trapezoid is average of the base times height. So if I were to write this in summation notation, it would look like this. And then when we're finding the heights, we're going to write f of xi xi plus f of xi plus 1 all over two, or sorry, times by change in x. So again, this part over here, it represents this base plus this base divided by 2 in order to find the average of your bases. And then this here represents your base. So the way we find the area of a trapezoid is its average of the bases. So this side plus this side divided by 2. So it is a little more work because instead of just finding one value and going across, you have to find 2. But it's really not too much more work. It is a little more accurate. Trapezoid approximations are not used quite as often. But again, it is still something that pops up. So you will want to be at least a little comfortable with it. All right. Now, basically, the way we make it more accurate and the way that we're doing this in order to actually find our integrals, this here is like the primitive version of finding your integrals. And so what we're saying is we're just approximating. So whether we're doing trapezoids or rectangles, whatever, it's still going to be really inaccurate. But we're saying what would happen if instead of doing like a bunch of intervals that are like, or instead of doing only 4 intervals, what if I took one at every 0.25, right? And I were to draw it out something sort of kind of like this. So every of these little tick marks, I'm drawing a new horizontal line. And these lines are all perfectly horizontal, as you can see. Yikes. Now, as you can see, it takes a lot more time, but your approximations are way closer than when I was doing left-handed approximations earlier, right? Like, even though when I have all of these, it just makes my approximations a lot more closer. Now, imagine if my approximations were even smaller, and I said instead of doing one, I was going to draw a new horizontal line every like third of a tick mark here. So I'm going to have like 3 triangles in this one little tick mark, or 3 rectangles, excuse me. That's the general idea here. We're saying what happens if we increase the amount of rectangles we have? If I have 4 rectangles, it looks something like this. And we're missing out all of this information. And I'm going to just do this like this really quickly. However, if I were to have something like this, where my rectangles were done every half, it would be like this. And even increasing the amount of rectangles by a factor of 2 just increases it that much more. That increases the accuracy by that much more. So again, it's still not amazingly accurate, but it's a lot more accurate than my orange one. I'm missing so much more information with my orange one than I am with my pink one, and I'm taking the same left-handed approximation. It's just a matter of now there's a lot more shapes. So basically, the big idea here is the more rectangles you have, the more accurate it is. And so what this is doing is it's saying I'm taking the sum, but I'm going to have an infinite number of rectangles, but that's impossible. So what we're saying is instead of getting an infinite number of rectangles, what happens if I take the limit as n approaches infinity? And this here, over here, this is basically the backbone of your integration. So when you're doing your fundamental theorem of calculus and you're doing that, your integration, this is basically what's going on. You're never going to write this out and actually solve the limit, really, but basically this is the idea of what you're doing. You're just adding the same thing over and over and over and over and over again. But the idea is you're making your rectangles smaller and smaller. Okay, so just to kind of take away, what we're doing here is we're working with Riemann sums in order to find areas under the curve. When we're doing integration, we're finding the areas under a curve for is closed interval. There are a handful of ways to do it. There's the left hand and right hand rectangle approximation where you start at either the left or right side and you just draw rectangles. There's the midpoint approximation where you go in the midpoint and you draw your rectangles. And then there's the trapezoid approximation where you connect each endpoint and find the area of the trapezoid, which is base 1, which is this, plus base 2, this, divided by 2, which is the average of your bases, times the height, which is this over here. And all of you guys remember that from geometry. The way we make this more accurate is we just add more and more intervals. Now, the way a question normally looks is it'll look something like this. Approximate the area under the curve from 0 to 4 using 6 equally spaced intervals, or equally spaced rectangles, some books say, using a right side Riemann sum. And the reason it's called Riemann is because Riemann was the guy who thought this up. Okay, so if you look here, I have 1, 2, 3, 4. It says I should be using 6 equally spaced. So the way that you figure that out is my total distance I need to travel is 4, and I need to split it up evenly into 6. So that's going to obviously give me a base of 2 over 3. So that's going to be my base over here. So at 2 over 3, I'm going to go 1, 2, that's right around here. And then that's where I draw my first one. And it says right-handed Riemann sum, so that's why I'm going to draw it like this. Okay, that is the super brief, basic overview, okay? I'm going to not expect you guys to know this for tomorrow. I'm going to go over a slightly more practice-based thing as far as we're doing integrals as well as derivatives or antiderivatives. So we're going to focus more on that next class to make sure that we're relatively solid with the mechanics of that. And I'm also going to field questions about this. So hopefully you watch this before tomorrow. If you don't, I understand, because it was my fault that I didn't, I wasn't there for your class. And so because of that, this is going to be pushed off till next week. Your next quiz is going to be next week, the first time I see you. It's going to be on basic integration rules and whatnot, both indefinite and definite integrals. And then you will have a test on Friday, but it's going to be kind of like a overview kind of thing, and it's not going to be like a test. It's not going to be a huge final. It's going to be very minimal, just as a way to kind of cap off, and it's going to let me see what you guys are working with. Okay, that being said, let me know if you guys have any questions. Again, this is really brief overview. It's 30 minutes, but still quote unquote brief. Okay, I'll see you guys later.